Welcome to a screencast on solubility equilibrium. The objectives of this screencast are to write chemical equations and equilibrium constant expressions to represent solubility equilibria and to perform calculations involving solubility equilibria. Now previously we saw that we can determine whether an ionic compound is soluble or not by referring to what are called the solubility rules. And when we do that, we can see that potassium nitrate is soluble and calcium phosphate is not soluble in aqueous solution. Now, the reality is that's kind of a simplistic way to look at things. In fact, both potassium nitrate and calcium phosphate are partially soluble. Potassium nitrate's much more soluble in water. Calcium phosphate is much less soluble in water, but both of them do have some ions in solution and do have some amount of solubility. Now, how do we deal with this kind of equilibrium? Well, the convention is that we deal with the equilibrium between an ionic solid and its aqueous ions in a saturated solution. So here we have some solid. It's got some dissolved ions. The solution is saturated, so no more ions can dissolve under these conditions. And our convention is we write the solid ionic compound on the left and then the aqueous ions into which it dissociates on the right. And then the equilibrium constant for this is called a solubility product constant. We symbolize it by K sub SP, SP for solubility product. And this is an equilibrium constant that can be determined experimentally and can be looked up in tables. Now let's take a look at an example of how this would play out. So silver chromate has a K sub SP of 9.0 times 10 to the minus 12th at 25 degrees Celsius. Let's write the equilibrium equation and the solubility product expression for silver chromate. Well, what we do for the equilibrium equation is we write silver chromate on the left as a solid, Ag2CrO4 solids on the left, and then a double arrow for equilibrium, and then it dissociates into 2 silver plus 1 charged ions and 1 chromate CrO4 minus 2 charged ion. And then the K sub SP is K sub SP equals the Ag concentration squared times the chromate concentration to the first power. Note, of course, we don't write Ag2CrO4 in the equilibrium constant expression because it's a solid. And then the product of these two concentrations is equal to 9.0 times 10 to the minus 12th. Now, all ionic compounds can have a determination of an equilibrium constant value. Here are some examples: barium fluoride, nickel carbonate, zinc 2 hydroxide, mercury bromide, cadmium sulfide, and lead phosphate, and their K sub SP values at 25 degrees are shown. Notice there's a pretty big range. Barium fluoride has a K sub SP of 2.4 times 10 to the minus 5th. Lead phosphate has a K sub SP of 1 times 10 to the minus 54th. And the larger the K sub SP value, the more the solid dissociates or dissolves into its ions, and so the more soluble that particular ionic compound is. And conversely, the smaller the K sub SP value, the less the ions dissociate and the less soluble the compound is. And so in general, the K sub SP value is a kind of rough and ready measure of how soluble or not soluble a given ionic compound is. Now, it turns out that stoichiometry matters as well, how many ions of each type this dissociates into, but certainly if we are comparing two ionic compounds of similar proportion in terms of their positive and negative ions, we could directly compare K sub SP values to determine which was more soluble and which was less. Now let's look at some calculations, how we deal with equilibrium for solubility and K sub SP and solubility actual calculations. So for this question, the solubility of silver bromide is known to be 7.1 times 10 to the minus 7th molar at 25 degrees Celsius. Let's determine the value of K sub SP for silver bromide. Well, first of all, we write out the equilibrium expression or equation. Silver bromide solid on the left, silver plus and bromide minus ions on the right. And then it's equilibrium, so we can use an ice table. Our initial is where we pretend that we put some silver bromide solution or some silver bromide solid into our beaker with water, and we pretend it hasn't yet dissociated. And then, of course, it will dissociate according to stoichiometry. So every one silver ion also produces one bromide ion, 1-to-1 stoichiometry. And so at equilibrium, whatever the silver ion concentration is, we'll call it X, the bromide ion concentration is the same. And now we note that the silver ion concentration, or for that matter the bromide ion concentration, is 7.1 times 10 to the minus 7th molar, because if we are given the solubility of silver bromide to be 7.1 times 10 to the minus 7th moles per liter, then 7.1 times 10 to the minus 7th moles of silver ion and 7.1 times 10 to the minus 7th moles of bromide ion dissolve in a liter of solution. So it's pretty simple now. K sub SP is the silver ion concentration times the bromide ion concentration. Both of those are 7.1 times 10 to the minus 7th. So that product of solubilities is 5.0 times 10 to the minus 13th. Okay, now let's look at another example. In this case, we're dealing with silver chromate, and we know the K sub SP for silver chromate. It was given in a previous example. It's lookupable in tables, determinable by experiment. And the K sub SP for silver chromate is 9.0 times 10 to the minus 12th. Now let's use that to find the solubility of silver chromate. Again, we set up an equilibrium expression, silver chromate solid on the left, silver ions and chromate ions on the right. Pay attention to stoichiometry, 2 silver ions for every chromate ion. We set up an ice table, pretending it hasn't dissociated initially, and then we let it dissociate, and every chromate ion that dissociates has 2 silver ions, so X and 2X respectively. And then at equilibrium, we have 2X for the silver ion concentration, X for the chromate ion concentration. And the K sub SP is equal to silver ion concentration squared times chromate ion concentration to the first power. So that's going to be the quantity 2X squared times X. And that product is equal to 9.0 times 10 to the minus 12th, the K sub SP value. So we have this expression to solve. It's going to be pretty easy to solve. 2x squared, quantity squared, is 4x squared times x makes it 4x cubed. And if we divide by 4 and then take the cube root, we end up getting x, which is the solubility, is equal to 1.3 times 10 to the minus 4th molar. Okay, now let's consider the equilibrium we just looked at, silver chromate and in equilibrium with its ions. And what could we do to change this to make, let's say, more precipitate or get something to dissolve more fully? And like with any equilibrium, if we mess with it, for example here, if we increase the concentration of silver ion, or if we increase the concentration of chromate ion, that's going to disturb or be a stress on the equilibrium. And if the stress on the equilibrium is increased concentration of products, the system will respond by making more reactants. And in this case, more reactants are the precipitate silver chromate. And so if we wanted to make more precipitate, we'd simply add some silver ion or chromate ion to our solution. Now, this is an example of something called the common ion effect. And the common ion effect is where the solubility of a slightly soluble ionic compound is decreased by the presence of a common ion in the solution. Now, it's worth noting that this is just another manifestation of Le Chatelier's principle. So we can remember a thing known as the common ion effect. It is talked about in chemistry terms, but it is simply an example of Le Chatelier's principle in action. So one last thing, let's see if we can predict whether a precipitate will form when we mix together two solutions containing the ions that could potentially make a precipitate. So in this case, we're going to mix together some silver nitrate, which is a source of silver plus ion, with some sodium chromate, which is a source of the chromate 2- ion, and let's see if we can figure out if a precipitate forms with the given amounts and concentrations. Well, we've done this kind of thing before, but there's a little bit of a new twist here. So we first of all have to state our equilibrium expression, silver chromate solid on the left, silver ions and chromate ions on the right. And we note that we know the form of K sub Sp and the value of K sub Sp for this reaction. Ksp equals silver ion concentration squared times chromate ion concentration, and that product is equal to 9.0 times 10 to the minus 12th. And if we want to predict which direction a reaction will go with given initial conditions, we've done this before. We determine a reaction quotient Q and then compare it to the equilibrium constant K, and we can do that here as well. So we'll determine a Q sub Sp, and the thing you do have to pay attention to is when you mix two aqueous solutions together, they dilute each other, and so their concentrations will actually decrease. So if we have equal volumes of the silver nitrate solution and the sodium chromate solution, they're going to dilute by a factor of 2, and so the 0.001 molar silver ion will actually be half of that, and the 0.002 molar chromate ion will actually be half of that. So the actual concentrations initially of the silver ion is 0.00050 molar. The actual concentration once diluted of the chromate ion is 0.0010 molar. And then when we calculate that, we get 2.5 times 10 to the minus 10th. Now the reaction quotient, Q, is a very small number, but 2.5 times 10 to the minus 10th is bigger than 9.0 times 10 to the minus 12th. So when we compare the two, the Q sub Sp is bigger than the K sub Sp, and if the Q is bigger, then the reaction goes to the left, and going to the left means forming more solid, or forming solid, which is precipitation. So because Q is greater than K, we can determine that precipitation will occur with these conditions. And that is it for the solubility equilibrium screencast.